Hi, this is Slav American from the Johns Hopkins University Applied Physics Lab, and I'm speaking on behalf of the team of our NASA Drive Science Center for Geospace Storms. You can find some information about the center in this press release, which you can find at this address. As I said, the Center for Geospace Storms, or CGS, is one of the NASA Drive Science Centers selected for Phase 1 study. The vision of our center is to transform the understanding and predictability of space weather. We plan to do so by developing a new model of Stormtime Geospace, which we call the Multi-Scale Atmosphere Geospace Environment. The model will include all key regions of Stormtime Geospace and in fact extend all the way into the lower atmosphere to include the driving from below. Another key requirement for our model is that it resolve a broad range of scales. And the reason for that is because we realize the importance of various mesoscale processes operating across the geospatial domains that are important for capturing the storm-time dynamics. The objectives of our center are in short, to innovate community modeling capabilities, to empower the models with data, and to discover how Stormtime Geospace works. And I'm going to expand on these bullets in the next slides. So our team is shown here. It's a diverse team of scientists with a broad range of age distribution, of different career levels, diverse expertise, and diverse science areas that the members represent. In particular, we have a large representation of both theory modeling and data analysis expertise, which is required to achieve our science objectives. So speaking a little bit more to the science objectives, the first one is to innovate the community modeling capabilities by building a physics-based predictive model of Stormtime Geospace, coupling all key regions and resolving critical mesoscale processes. As I said, we call this model the MAGE model, and I'll talk in more detail about the model in a subsequent slide. The second objective is to empower the MAGE model by ingesting heterogeneous data sources and developing rigorous validation methodologies using multivariate data sets. What we mean here is that, as is known to the CEDAR community, the advent of distributed global data sets, such as the data sets representing the ionospheric electrodynamic quantities, for instance, these data sets present new opportunities for data model fusion and also for rigorous model validation. And furthermore, both space and ground-based observations are so disparate that they provide their measurements at different spatial and temporal resolutions, which really requires synergistic effort from model developers and data analysts to be able to properly employ the data to devise proper conditions for assessing model fidelity, and also to ingest or assimilate these data sets into our models. So for these reasons, as I said, the team involves both model developers and data analysts, and we plan to robustly test our model with the data sets and techniques to verify model capabilities across the geospace domains and critical scales. Finally, we will apply this model to solving mysteries of Stormtime Geospace. To be specific, we will discover, understand, and quantify the causal connections and emergent dynamics across spatio-temporal scales, domains, species, and energy populations characteristic of Stormtime Geospace. As I said, we realize the importance of various mesoscale processes and their role in cross-scale coupling in global scale dynamics that emerged during storm time. We have identified a number of issues of potential CGS focus, which include injection of plasma sheet particles into the ring current by bursty bulk flows. The reason it's important to the CEDAR community is because the buildup of the ring current then leads to the generation of region 2 currents and their closure in the ionosphere, together with the region 1 distribution, modulates the closure of the currents in the ionosphere and the delivery of the Poynting flux and heating into the ionosphere and thermosphere. Furthermore, we are interested in ionospheric polar cap patches and tongues of ionization, both for their space weather effects, but also from the point of view of horizontal plasma transport, as well as electrodynamic and mass coupling to the magnetosphere. And finally, we will include the preconditioning from the ionosphere-thermosphere by lower atmospheric processes. Now, that said, we are happy to hear ideas and suggestions from the community for problems that we can address together. And for this reason, we included a link at the end of this slideshow where you can provide your feedback. So this slide demonstrates our vision for the MAGE model. This is our long-term goal, and at this stage we are addressing parts of this diagram, as I'll speak about in a few next minutes. The main models that will provide the backbone of this coupled model are a global magnetosphere model, which is called Gamera, as I'll describe in a second, and the NCAR model that extends from the lower atmosphere to the ionosphere, WACAMX. Since WACAMX is better known to the CEDAR community, I'll spend a few moments to talk about Gamera. You can find more information about this model at this website, but in a nutshell, it's a reinvention of the high heritage Lyon Feder-Mowbray global magnetosphere model. And the model itself has been described, the algorithms for Gamera have been described in this paper, and very recently this paper describes the magnetospheric version of Gamera. As I said, in phase 1 we're striving to achieve a part of this MAGE vision. We call this coupled model that we are developing in phase 1 mini-MAGE, which is the coupling of Gamera, the rise convection model, and the TIGCM model, which will in phase 2 be replaced with WACAMX. I've talked to these bullets already. I will only mention here that we do plan to make the MAGE model available to the community as we develop this project. So in the following few slides, I would like to give a few science highlights that will be discussed in more detail by my colleagues that are on this team during the CEDAR week. And as you will see the name and the corresponding sessions where the person will talk in the upper right corner. So this is the first highlight where we compare the simulation from the mini-MAGE model as well as the version of this model without the ring current component, without RCM, so just coupling Gamera and TIGCM. Here you see the northern polar cap field line currents for a storm time simulation. This is approaching the peak of the main phase of the storm that occurred in the August of 2011. This is from the Anderson et al. Paper that was published in 2017 that compared ampere currents with a number of models, both empirical and physics-based, that were available at CCMC at the time. Here you can see the results of both Minimage and, like I said, Minimage without the RCM, and you can see that the Minimage model does a very good job of reproducing the ampere currents. We're pretty excited about these results. However, I should mention that right now the resolution at which we're running this model, as is shown here, is not the peak resolution that we're planning in phase 1. So in phase 1 we plan to double the resolution in all of the domains covered by the Minimage model. Another highlight is shown in this slide. This now provides the comparisons of the thermospheric density with the CHAMP and GRACE spacecraft. This is for a different storm that occurred in August 2005. This presentation will be discussed later during the week by Kevin Pham. Again, as you can see here, the model does a very good job of reproducing all of these peaks in the thermospheric density at both spacecraft. And if you follow the spacecraft in the movies in both hemispheres, you will see that each peak corresponds to both temporally and spatially varying peaks of density, which are occurring because of the spatio-temporally varying inputs at high latitudes from the magnetospheric model, Gamera, and RCM. As the movie plays, you will see that toward the end of this movie, which is the recovery phase of the storm, particularly at CHAMP, the densities will be over predicted by the model, and so we definitely have more work to do. We're far from being done, but these initial results are very encouraging to us. I'll let the movie play toward the end before moving to the next slide. Here you can see that some of the peaks, like I said, will be over predicted. Okay, moving to the next science highlight. This talk will be given later in the week by Dong Nguyen from NCAR. This result is about the SAPS, which is the subauroral polarization stream. All of the dial plots here show you the northern hemisphere for the various quantities shown at the top of the corresponding plots. This is now a Gamera RCM simulation, so there's no TIE-GCM. The background EUV conductance comes from an empirical model, and this is for the St. Patrick's Day 2013 storm. There are a number of very important details about the model here, which also apply to the model results in the previous slides. Number one, the model includes a diffuse precipitation that was derived from the election population in the RCM model. This is important for a number of reasons. First of all, it provides us with a realistic downside precipitation pattern and therefore conductivities, but also it provides a very sharp drop-off at the equatorward edge, which is important for reproducing SAPS. The model also includes a dynamic plasmasphere that is evolved by the RCM code and then passed to our global magnetosphere code, and also a realistic ring current which drives significant region 2 currents in the ionosphere, which are importantly occurring at pre-night equatorward of the precipitation boundary here, which results in a very pronounced secondary peak of the electric field, which can be interpreted as a subauroral polarization stream. So this slide shows the benefits that we believe CGS brings to both the scientific community and beyond. In short, we're addressing a grand science challenge. We believe we're empowering the heliospheric community by providing an open source whole geospace model to the community. We are working with our partners at the major universities with space physics programs to bring up a new and diverse generation of scientists. We are supporting NASA and NSF programs by being synergistic with their goals. And finally, the project obviously advances space weather preparedness of our nation. Finally, this is my last slide. This is basically our call for community feedback. As I said, we're open to your suggestions about well, everything, but also in particular the science questions and feedback on the science that we want, that we can address together. Please feel free to go to this webpage. It has a form which you can fill out, and that will be sent to us. You can also directly email me at my email address as is shown here. And finally, to bring to the community's attention, we will have our first CGS workshop in November of this year, 9th to 13th. We're planning to have 1-2 days during the week open to the community, and you know, at this point, for the obvious reason, we don't know whether it will be in person or virtual, but we will definitely have either option available, and we are working on details and logistics as we go on. Thank you very much for your attention.